This is a video that almost didn't make it, and you'll understand why in just a little bit. In dealing with this project, we had to face a lot of the same challenges that researchers in physics, chemistry, and medicine face, and I'm going to draw out some of those parallels as we move through the video. Probably the most fundamental question is, how do you select a topic to either research or do a video about? It starts with observing the world around you with a healthy level of curiosity and looking for something that's important, significant, and at the same time maybe the basic principles are not well understood or there are conflicting explanations for what's going on and you want to get to the bottom of it. Now on one extreme, you can pick topics that are in the news. They're hot topics, everybody's talking about them. From a researcher's point of view, you're more likely to get grant money or support from your department. As a YouTuber, you get more views. On the other extreme is a topic that's interesting or fascinating to you, but you don't care about anybody else's opinion. One strength of that narcissistic approach is that it focuses your energy. So even after you leave the shop or the lab, you're still thinking about it, trying to solve problems, figure out a better way to do something, and explain what your findings are. Probably the best location is to be somewhere in the middle. Pick a topic that's interesting to everybody, including you. Once you've sort of gotten an idea about what you're going to do, then you begin the deep dive. You go online, you look at the research papers, you talk to colleagues, you watch YouTube videos, and you form a plan. Now, this particular plan started out a couple of years ago when we obtained this warehouse. The previous tenants had an online resale company where they would buy overstock or discontinued items, repackage them, and then they would sell them online or on eBay. And when they were leaving, they still left a fair amount of inventory behind. And they said, look, we could hire a couple of guys, a couple of trucks, find a storage facility, and move everything out. But because the cost of doing that would be similar to the value of the inventory, they said, look, on the other hand, we could just leave it. So we took a quick look around and we found that there was some pretty good stuff there, so we said, leave it. In that inventory was a whole bunch of ceiling fans. These are the kind that you can buy at Home Depot or a lighting store. Some of them look pretty cool. Some of them look a little bit like they belong above a poker table in a saloon run by a lady called Kitty. Tacky. But almost universally, they share one property. The rotor blades are stamped out of particle board, and then they'll apply paint or decals for aesthetic purposes. But inherently, they're just slabs of wood. They're aerodynamically awful. So what occurred to me is what would happen if you just replaced the rotors with real good quality airfoils? Could you decrease noise levels, decrease power consumption, and improve air movement? So that was the idea. So I went ahead, went through some of the boxes, found some good examples. They're all fairly similar, and took out one of the best motors I could find, and then removed the ancillary lighting and the fixtures and left basically just the motor and the rotor. I then mounted it on this test stand, which is just a post of metal that is stabilized by these Kevlar lines to turnbuckles that allow me to provide lateral support as well as level this to make it very easy and very reliable as a test site. Then I fabricated 2 additional rotors that you can see on the table behind me. Now, all 3 rotors have exactly the same diameter. But the first one is a simple curved blade, a metal blade. This is in fact an airfoil, and it's not that different from the airfoil that was used by the Wright brothers at Kitty Hawk. It's a decent design. The other rotor, I'm going to come around here to show you a little bit better, is an NACA asymmetric airfoil design. This means the bottom is flat and the top is curved, and you can see that same shape here in the sides of the rotor. And it is optimized for low speed operation, which is what we're going to be doing here. The reason I selected these 2 particular airfoils to compare is because they're super easy to construct. So if this turns out to be a successful test and you wanted to replace the blades in your fan, I can show you very easily how simply you can put this together. It's inexpensive and it's quite easy to do. So to do the testing, I set up a stand here that has a power meter that registers how much power we're consuming by the fan. I have a decibel meter that measures sound pressure. And then I also have a handheld anemometer that measures airflow velocity so that we can compare the different units. So let's get started. I'm going to turn on the fan, and for the first few seconds as it accelerates, the power levels are going to fluctuate a little bit, but once it's stabilized, then we'll take our readings. Okay, so we're going to call it 64.3 watts, and the sound level, 40 decibels. And then the air velocity, I'll hold this here. One meter per second. All right, let's go ahead and test the other rotor. All right, we're going to test the metal blade. Let's go ahead and turn it on. Let it stabilize. Noise level. .40 decibels. And airflow. I would call it 0.7, 0.6 to 0.8, so 0.7. Might even be generous enough to call it 0.8. Now let's try an asymmetrical airfoil. Okay, now we have the asymmetric rotor. Let's go ahead and turn it up. Again, we're going to let it stabilize before we do our reading. Okay, 65 watts. Sound level. .41 decibels. Makes sense. This thing does seem like it's flowing a little bit faster. So 115 to 129. Let's call it 1.2 meters per second. So, obviously, the simple metal airfoil, not so good. The classic asymmetrical airfoil, it's better, about 20% better. Now you might think, well, is that really that much of a difference versus the slabs, 20%? Well, actually, it is pretty significant, because all of the diameters of the rotors are exactly the same. So when the blade is moving the air 20% faster, it's moving 20% more mass through. And so I'm going to give you a little bit of physics here. And I promise this is the only equation I'm going to write. But this is the classic kinetic energy equation that describes how much energy is present in a mass that's moving. So if we went from the standard paddle blades, 1 meter per second, to this airfoil blade at 1.2 meters per second, that means we're moving 1.2 times as much mass through that column of air. We're moving it at 1.2 times the velocity, times 1.2 because it's square, or in other words, 1.2 cubed. That is approximately 1.78, I believe, and let's call it 80% more energy is actually present in the air column that's being moved by the asymmetrical rotors. So it is a significant improvement in the performance of the fan. There's a problem though. You see, when you go in your shop or you go in your home and you turn on your ceiling fan, probably the last thing you're thinking about is the kinetic energy equation. You're thinking, how loud is it? How much power does it use? And how fast is the air moving? A 20% improvement is not insignificant, but is it worth it? Well, as easy as these things are to construct, and the fact that I obviously like to build things, I'd probably say no. I probably wouldn't do it. So I was kind of disgusted and I just turned off the lights and went home. But it was bothering me. It just kept sticking with me because it's 20% improvement going from a slab, a barn door, to a quality airfoil. It seems kind of low to me. Kept going over in my head. I couldn't get past it. And a couple days later, I just said, no, I got to go back. I've got to retest this. I got to find out if I made a mistake. So I came back and reperformed the test twice. And the result? Exactly the same. There's an old, humorous definition of insanity. Doing the same thing over and over again and expecting a different result. But like I said, it was driving me crazy. Nevertheless, I decided, this isn't going to make it. We're not going to make a video about this. It's not significant enough. So I started disassembling all the parts. I'm going to put it on a shelf, maybe use it for a future project or another video. And when I eventually got down to taking the motor off of the stand, I noticed how warm it was. It wasn't burning hot, but it was well above body temperature. And this was maybe 20 or 30 minutes after I finished the testing, so it had been hotter before. And then, bing! The moment every researcher lives for, the epiphany. So I went ahead and I reset up all of these parts to perform one more test without any blades at all. Understandably, I probably should have done that at the beginning as a control for these tests, but better late than never. Okay, the rotors are off. Now let's run this test and just see how much power we use. 53.7 watts. Call it 54 watts. Aha. The fact is that the underlying motor is wasting over 80% of the power that we were using for these tests in heat. The difference between the rotor functions is real, but it wasn't out of 67 watts that it was making this differential performance. It was out of basically 11 or 12 watts. All of the rest of the power was being wasted in the motor itself. So it turns out that the elephant in the corner of the room wasn't the rotors, it's the motors. So I went online and tried to find a brushless DC version of this type of fan. It's a bit of a niche item, and so it's a little harder to find them, and they will cost you maybe 20% more, 25% more than the basic AC fans. But from Hunter Fan, I was able to find a replacement, and I'm going to go ahead, set this up on a stand, and show you what it looks like. Okay, you can see that the motor is very similar in its form factor. It actually weighs the same amount. And the only real difference between an AC motor and a brushless DC motor, this permanent magnet motor has some installed magnets in it, which theoretically should increase the cost of the motor a little bit. Otherwise, the components are pretty much interchangeable. In addition, if you can look down, I don't know if you'll see this clearly, but right at the base is a small electronic control box that allows me to actually use a little remote. So it's got a little bit of an advantage there. The additional cost of those electronics nowadays is probably $1 a piece, and the magnets in there. So the justification for the increased price probably is just due to the fact that not a lot of people bother to buy them. Let me show you how well this performs. I'm going to go ahead, turn it on, and we're going to see what happens. Now, give it a little more time to stabilize. Watts versus 55 watts. It's an enormous difference in efficiency. So let's see how this holds up when we compare it with the rotors on. All right, let's just check those. That looks good. All right, let's go ahead and see what this does. Now the electronic controller takes a little bit of time to say, I want to start. There's a little thinking involved. We'll let this stabilize and then we'll get some numbers. I have this up at full speed. Still accelerating. All right, that looks like full speed. Let's look at the noise level. About 48 decibels. Look at the power level, 57.8 watts. Let's take a look and see what the velocity is. Call it 1.8 meters per second using about 7 less watts. So enormously more efficient. Now I'm going to make a little bit of an adjustment here, and I'm going to slow the fan down to try to produce a comparable 1 meter per second velocity out of the rotor. And then we're going to look at sound level and power consumption. Okay, so it's 1 meter per second to 1.15. It's a little bit higher flow than the other one. Sound level is 40 decibels, exactly the same. But look at the power consumption, 23 watts. That's 44 less watts than we were using before. This is really a huge finding. Not only is this more efficient, but it's the same volume in terms of sound level, and it also gives you some additional control in terms of speed with the wireless. So it's kind of a nice deal. Now, the reason this is such a huge issue is because if you're like me, we use our ceiling fans 24/7 to circulate and keep the air nice and fresh. And if you're using 40 watts continuously just to waste it inside of the motor, in one day, 24 hours, that's about 1 kilowatt hour. In New England here, that costs about 24 cents per day, or about $90 per year. The slightly higher cost of this fan will be paid for in about 6 months. And how frequently do you repair your broken ceiling fans? They last a very long time. So in a decade, you could potentially, with this one fan, save $1,000 in electrical costs just from one fan alone. Now, to be fair with this, AC motors can be built as efficiently as permanent magnet DC motors. If you're building an aircraft carrier or you've got multi-thousand horsepower electric motors in your big industrial plant, there are electronic control systems that will let that work. But in these legacy small stamped out motors that are made for appliances all over the world, that isn't the case. And that is why this is not just a significant finding, it's a huge finding. Because these same type of motors are present in your washer, your dryer, your refrigerator, your freezer, the blowers in your air conditioner, your furnace, they're everywhere. So if that kind of consumption is present in all of these motors in all of the homes within the entire population of the planet, we're talking about terawatt hours of consumed electrical power. If you're interested in sort of electrical and energy efficiency, and you promote nuclear or fusion or hydroelectric, air, solar power, that's great. On the production side, we want to maximize efficiency. But wealth isn't just how much money you make, it's how much money you spend. If we could simply save that kind of level of power by evolving into more efficient motors, it's a perfect match. And I think that is what makes this a very significant video and why we ended up posting it. I hope you found this interesting. And in addition to this, if you have any kind of questions or any comments about what we've been doing here, please put it in the comments section. I read them all and I try to answer as many questions as possible. In addition to that, if you really like what we're doing, please subscribe, because it pushes the YouTube algorithm to distribute our videos to a much broader audience. And the larger we get, the more we can afford to do. If you really like what we're doing, take a look at the Patreon link and you can provide direct support. Every dollar that we get into the channel is spent on the channel. And we've got some really great ideas on the table and we would like to develop them. So I really want to thank you for watching. So in any case, you take care, have fun, stay cool, and we'll see you soon.